Now let's discuss problem solving with trigonometry. Most of the time, trigonometric ratios are used to solve real-world problems, and there are some key vocabulary words that you will see in these word problems. Two of them are the angle of elevation and the angle of depression. The angle of elevation is the angle above the horizontal to an object. So when a person is looking upward, it's between the line of sight and the horizontal to them. For the angle of depression, the observer is instead in the air, and there's a horizontal going straight out from where they are, and then the angle of depression is between that horizontal and their line of sight when they are looking down at an object. And both the angle of elevation and the angle of depression are measured relative to parallel horizontal lines, making them equal in measure. So here we can see that horizontal distance between the pilot of the plane and looking down at the ship, that angle of depression, if we say it's 20 degrees, then the angle of elevation from the ship to the plane in the air to the horizontal formed by the sea is the angle of elevation. And because both lines of sight are horizontal to one another, creating parallel lines and alternate interior angles, the angle of depression and the angle of elevation are equal in measure. It's worth noting that this model imagines the Earth to be flat, or where objects are close enough so that the distance being traveled appears to be horizontal and relatively flat. Here's another example. You are standing 200 meters away from the base of a building. You measure the top of the building to be at an angle of elevation, or the angle between the ground and the line drawn to the top of the building, to be 60 degrees, and we need to find the height of the building. Let's begin by making a quick sketch showing the original right triangle and the one showing the appropriate trigonometric functions. Remember, we have the sine of our theta 60 degrees being the vertical distance, and the cosine of 60 degrees being the horizontal distance, where the length of the hypotenuse in the smaller model triangle that we're drawing being of length 1. Then we can set up the ratios, substitute the values that we know into the proportion, and solve it. So we have the height, h, which is unknown, over its horizontal 200, and that is equal to the vertical here, which is sine of 60, over the cosine of 60 degrees. So we did height to horizontal, height to horizontal. And then if we cross multiply, we get that h times the cosine of 60 degrees is equal to 200 times the sine of 60 degrees. If we divide both sides by cosine of 60 degrees, and then substitute these values into a calculator, 200 sine of 60 divided by cosine of 60, we get 346 and 41 hundredths. And it's in meters. Well, some of you may have also thought, well, hey, I have sine of 60 over cosine of 60. Couldn't I also use tangent? You actually could. You could also type into your calculator 200 times the tangent of 60 degrees and get the same exact answer. And here we can see they noticed that height to distance was equal to tangent also, and they used tangent of 60 degrees right away. That is also a possible method for solving this problem. We often have to measure angles of elevation or depression in order to solve problems. There are very accurate ways of doing so, which are used by surveyors, navigators, and others, but you can make a simple device called an inclinometer to accomplish the same thing, and then solve the problems on your own. Just tape a protractor to a meter stick and hang a small weight from the hole in the protractor. Then set it up so that when the meter stick is horizontal, the string goes straight down and points to or passes through 90 degrees. Then if you look along the meter stick as you're holding it up to your eyes at an incline, you can hold the string where it touches the protractor and read the angle. You'll have to subtract the angle measured from 90 degrees to get the angle to the horizon or the angle of elevation. Some of you may be asking, well, why do I have to subtract it from 90 degrees? Well, that's because the angle that is being read by the inclinometer is actually this angle right here. I'll call it the Greek letter alpha. That's what the inclinometer is reading. The angle of elevation that we want is this angle right here, theta. And we have formed a right angle right in here by drawing the horizontal to the vertical string. So we have 90 degrees in here. And we know that 3 angles of a triangle sum to 180. So we have that alpha plus theta plus 90 degrees is equal to 180. If we subtract 90 from both sides, we'll get that alpha plus theta is equal to 90 degrees. And then if we're looking for theta, our angle of elevation, we're going to subtract alpha from both sides and get that it's equal to 90 minus that alpha reading from the inclinometer. Here's an example. You are standing on the ground and look along your inclinometer to see the top of a building at an angle of 30 degrees. Let's actually start drawing a picture. So here's a person. Here's their horizontal line of sight. And here's the building that they're looking at. Let's try to make the bottom of the building be even with the person and on the ground. We're told that the angle between the horizontal and their line of sight, or the angle of elevation, is 30 degrees. And the distance to the base of the building is 30 meters. So this is 30 meters. Here's a right angle. Find the height of the building. We need to find this total height here, which is actually going to be this unknown value x here, plus the height of this person, or the height of their eye above the ground. It's 5 feet. So this h is equal to x plus 5 feet, but wait a second, this is in meters. So let's convert the 5 feet to meters by dividing it by 3.28 feet per meter. And since we have feet per meter in the denominator, we can multiply the top and bottom by meters over feet, and anything over itself is 1. That will cancel out all of the units in the denominator, and then the feet will go away, and we will be left with 5 divided by 3.28, which is about 1 52/100ths of a meter. So this h is going to be equal to x plus 1 52/100ths. All right, so let's actually now figure out our similar triangle ratios that we're going to be using. So we've been drawing and putting in our ratios. The angle down here is still going to be 30. And then this is going to be the sine of 30 and the cosine of 30. So we have sine of 30 over the cosine of 30 is going to be equal to x, because that's the triangle's height over the triangle's base, which is 30 meters. And if we cross multiply and divide, we will get that x is equal to 30 meters times the sine of 30 degrees divided by the cosine of 30 degrees. And when we evaluate that in a calculator, we get 17 32/100ths. Some of you may have said, hey, wait, I have sine of 30 degrees over cosine of 30 degrees, and that's equal to tangent. So I'm going to do 30 times the tangent of 30. That's also 17 32/100ths. And then in order to get the final height, we need to add up the 17 32/100ths and the 1 52/100ths that we found earlier, so to make the final height be 18. So the final height's 18 84/100ths meters. And in this pull tab, they used tangent. When solving problems with trigonometry, you often find a right triangle that is similar to the one below. We have the sine of theta corresponding to the vertical distance and the cosine of theta corresponding to the horizontal distance. And when doing so, you find the solution by setting up the ratios of a proportion. So we have height over distance, that's one ratio, is equal to the ratio in this triangle, sine of theta over the cosine of theta. And some of you may be remembering that sine of theta over cosine of theta is equal to tangent of theta. So you could also use height over distance as being equal to the tangent of theta. However, since the hypotenuse in this triangle is 1, it's often forgotten that these are ratios and we are setting up and solving a proportion.